Hey, so I heard some good feedback from some of you guys about what we've been doing on Khan Academy. I didn't really explain it super well in the emails that I was sending out, but I just wanted to let you know we weren't going to be doing that for the rest of the school year. I just wanted to kind of see how it went and let you guys get used to it just as another resource for you guys as we're going through these chapters to finish the school year for the next little over a month. I'm going to be, for the most part, sending out videos again of your guys' lessons, but kind of as an extra resource with those, I might give you some of the little quizzes and things from Khan Academy. It's also a great resource for you guys if you're having a hard time understanding something that we're going over. You know that you can go back there and look through their videos, do some practice problems on there. But again, I really just wanted to make sure that you guys understand how to use it as a resource so that moving forward you can use it. So today we're actually going to be going back a little bit. What we were doing on those Khan Academy lessons was actually chapter 10, but we're going to be going back and doing chapters 8 and 9 now. So chapter 8 is going to be on monomials and factoring. And so let's get started on today's lesson. So monomials and factoring, some key vocab words here. Again, if I'm moving through these too quickly, you can always go on to Schoology. These are up on there. These words are also straight out of the book, so you can be following along in chapter 8.1 if you need to. So we have prime numbers, which are whole numbers greater than 1, for which the only factors are 1 and itself. That's something that you guys have been working with for a while now, so you should know that one. The opposite of prime numbers, if a number isn't prime, then it's a composite number, which means that it's a whole number greater than 1 that has more than 2 factors, so more than 1 in itself. Prime factorization is when we take a whole number and express it as the product of prime factors. When we get into our example problems that I'm going to do on the board here, the first thing that we'll be doing is dealing with prime factorization. Then we have factored form, which is when a monomial is expressed as the product of prime numbers and variables. No variable has an exponent greater than 1. So again, it's just broken down into all of its prime factors. Then a greatest common factor, which today you'll see written as GCF, is the greatest number that is a factor of 2 or more numbers. So a monomial is something that looks like this. It's a combination. Again, we've talked about this before, but just a reminder, it's a combination of numbers and variables by multiplication or division. They do not involve addition or subtraction. So for this monomial, negative 12a squared b cubed, they tell us to factor each monomial completely. Again, this is doing the prime factorization. So what we want to do here is the variables are going to be easy. We're going to save that for the end, but we're going to work with the number to start with. So I'm going to do, if you guys remember, this is called a factor tree. So I'm going to take my number, negative 12, and I'm going to break it down into its smallest, I'm going to do the prime factorization, break it down to the smallest numbers that I can. So negative 12 would be, we could do 2 times negative 6. 2 is a prime factor, so that's as far as we can take it. Negative 6 could be 2 times negative 3. Now when you're factoring these, if you end up with a number like negative 3, a negative number greater than 1, then you want to break that down to negative 1 times the number. So again, we had negative 3, so we broke that down to negative 1 times 3. So now what I can do is I've broken this down as far as I can go. 2, 2, negative 1, and 3. None of those can be broken down any further. So this is the prime factorization. We've factored negative 12 out to negative 1 times 2 times 2 times 3. If you multiply those all together, you end up getting back to negative 12. Then again, like I said, For the variables, it's pretty easy. A squared means that we have a times a, so we would say times a times a. B cubed means that we're going to multiply b 3 times. And that is the prime factorization of negative 12 a squared b cubed. Again, like we talked about on the last slide, the factored form, nothing is going to have a variable greater than 1. So that's why we had to break up the a's and b's. Now, when we have one that starts like this with a negative number, the other way that you could go about doing it, instead of having to get down to the end and taking that negative 3 and breaking it down to negative 1 times 3, you could, if we had the same thing, negative 12 a squared b cubed, you could just start by putting a negative 1 and then do your factor tree of just 12 instead of negative 12. And then again, just like we've talked about a lot in math, most of the time when you're doing math problems, there is more than one way that you can break things down. So up here we did 12 as 2 times 6. We could also go 3 times 4, and then 4 breaks down to 2 times 2. And then we still end up with our negative 1 we started with, then 2, 2, and 3, and then the same a times b times b times b. So we end up with that same factored form. So let's do another one down here. We've got 38rs squared t. So I'm going to take, again, my 38, and I want to do a factor tree with that number. So if I break down 38, I can do 2 times 19. 2 is a prime number, so I can't break that down anymore. 19 is also a prime number, so that's the whole factor tree for this one. So I would go 2 times 19 times r times s times t, and that would be my factored form. Now again, I have 2 s's because up in the original monomial, I have an s squared. One more we'll walk through together here. Negative 66 pq squared. So again, that negative 66, I can go ahead and just put a negative 1 right off the bat. And then when I do my factor tree, I'm going to do it for 66. So for this, I could go 6 times 11. 6 breaks down to 2 times 3. 11 is already a prime number. So I would have negative 1 times 2 times 3 times 11 times p times q, and that would be my factored form. Again, I want to take this factor tree down to where I have all prime numbers. Once they're all prime numbers, I like to circle them because it makes me know exactly which numbers I need to use. Otherwise, I might get confused and include 2, 3, 6, and 11. So I like to circle those numbers at the very ends of the factor tree, and that helps me remember which numbers to put into my factored form. So again, that's prime factorization of a monomial. So then the next thing we're going to do is the greatest common factor of a set of monomials. So in order to find the greatest common factor of a set of monomials, here we have 2 monomials, 17d cubed and 5d squared. So in order to find the greatest common factor between these two, which again is this largest number that is a factor of both of these monomials, or can be multiplied into both of those monomials. So in order to do that, I need to write out the factored form or the prime factorization of each one. So I have 17d cubed. Now if I take 17 and do my factor tree, all I can get is 1 times 17 because 17 is a prime number. So this would be 1 times 17 times d times d times d. Then for 5d squared, if I think about it, 5 is a prime number. Only 1 in itself go into it, so I can just go 1 times 5 times d times d. Then I want to look between my factored forms, and I want to find anything that they have in common. And I'm going to circle whatever they have in common. So they both have a 1, and they both have 2 sets of d's that they share in common. So what I'm going to do then is I'm going to take what they have in common, and I'm going to multiply those by each other. So 1 times d gives me d squared, which means d squared is the greatest common factor between those two monomials. So again, I just broke each one down to its factored form and found anything that they have in common. Now the same thing can be done even if you have 3 monomials. So we have 42a squared b as our first one. So I'm going to take 42, break it down with a factor tree. 2 times 21. 21 becomes 3 times 7. So this would be 2 times 3 times 7 times a times b. Then I have 6a squared. Now we could break 6 down with a factor tree, or if we just think about it, 6, all it can break down to is 2 times 3. So that would become 2 times 3 times a. And then 18a cubed. If we do a factor tree for 18, 3 times 6, 6 becomes 2 times 3. So we would have 2 times 3 times 3. Then we have a cubed, so times a times a times a. Now again, we want to go through, now that we've got them all in their factored forms, and we want to find everything that they have in common. So they all have a 2 in their factored form. They all have a 3 in their factored form. This one has a 7, this one has a 3, but they don't all have those, so we can't use those. Then we've got 1 set of A's, 2 sets of A's that they all have in common. So they all have a 2, a 3, and 2 A's. So what we can do is we can multiply those all together. 2 times 3 times A times A. So 2 times 3 gives me 6. A times A gives me A squared. So again, that tells us that 6a squared is the greatest common factor. That is the largest number that can be multiplied into every single one of those monomials. Now, if you feel like you're pretty comfortable with this and you can take a little bit of a shortcut, if we've got these 3 here, 12qr, 8r squared, and 16rs, if you look at just the numbers, again, I don't really recommend this, but if you can do this, awesome. It's always good to go back and check your work just to make sure. But if you think of 12, 8, and 16, and we think of the largest number that can go into each one. So let's see, 2 goes into all of them, 3 does not go in, 4 goes into all of those numbers, nothing bigger goes into all of those numbers. So we could say that 4 is the greatest common factor for the numbers. Then this one has a Q, but these don't, so they don't share a Q in common. We've got an R, R squared, and an R. So they do all have an R in common. and then this one has an S, but the other two don't. So the greatest common factor there would be 4 times R. Then, one special situation that we can run into here, if we take this, we have 25n, which if we take 25, and if we think of that with a factor tree, 25 breaks down to 5 times 5. So this would be 5 times 5 times n. And then we have 21m squared. So 21 breaks down to 3 times 7. Those are both prime numbers. So 3 times 7 times m times m. Now if you look at this, 5 times 5 times n and 3 times 7 times m, there is nothing that those have in common. So our greatest common factor here would be 1, because 1 does go into both of these. And what that means, if the greatest common factor between two monomials is 1, is we would call these relatively prime. So the reason we call them relatively prime, they're not prime because we see that neither of these are prime numbers. They both have more than one factor that goes into it, but they are relatively prime because there is no number greater than 1 that goes into both of those. So if you come up with this situation, you could have two different answers. Your greatest common factor could be 1, or you could say that those two numbers are relatively prime. So an application here of using the greatest common factor, the areas of two rectangles are 15 square inches and 16 square inches, respectively. The length and width of both figures are whole numbers. If the rectangles have the same width, what is the greatest possible value for their widths? So if we think of this, we have one rectangle that has an area of 15 square inches. So we could have a rectangle that's 5 inches by 3 inches, or we could have a rectangle that's 15 inches by 1 inch. Those would be our two possibilities there. For our second rectangle, that's 16 square inches, we could have one that's 4 inches by 4 inches, or our other possibility, not a very good rectangle, but 16 inches by 1 inch. Now we know that both of them have to have the same width. So what is the greatest possible value for their widths? We have to look at this and see what is the greatest common value. What's the greatest value that they have in common here? And in this case, it would be 1. So we would say the greatest possible value for their width would be 1 inch. Now, this was one way of doing the problem, was by drawing out diagrams. The other way that we could have done this problem is doing the prime factorization like we did on the last couple slides. So we could take 15, and we know that breaks down to 3 times 5. Then we could take 16, which breaks down to 4 times 4, we know, but those 4s can still be broken down, and 16 becomes 2 times 2 times 2 times 2. Now we look at this, 3 times 5 for 15, 2 times 2 times 2 times 2 for 16. There's nothing they have in common. So just like that very last problem we did on the last slide, these two numbers are relatively prime, which means that the greatest common factor would be 1. So another example of this, looking at it through the prime factorization instead of drawing out diagrams, What is the greatest possible value for the widths if the rectangles described above have areas of 84 square inches and 70 square inches? So what we're going to do here is write out our prime factorization again. We have 70, which breaks down to 7 times 10. 10 breaks down to 2 times 5. So this becomes 2 times 5 times 7. Then we have 84, which breaks down to, let's see, that could be 2 times 42. 42 becomes 2 times 21. 21 becomes 3 times 7. So we could go 2 times 2 times 3 times 7. Then just like we did before when we were finding greatest common factors, we're going to find everything they have in common. So here we would go 2 times 7, which would be 14. So 14 inches would be the greatest possible width that they could both share in common. So again, an application there, a real-world application of when we would use greatest common factors. So that is our lesson for today. Here's your homework. This will also, again, be up on Schoology like I would normally put it up. Like I've said many, many times, feel free to reach out, email, text, call. We can set up a time to get on Zoom. Some of you have done a great job of letting me know if you need help. And I've been able to get on Zoom with you guys to help you out with some problems. So feel free to keep doing that. And yeah, there's your lesson for today.